Hello, this is Kerry Schutz from MathWorks. In this video, I'm going to show how to apply the double cross-spectrum transfer function measurement technique to a buck converter. In a previous video on this similar topic of transfer function measurements, I introduced the double cross-spectrum measurement technique and applied it to a very simple single-pole low-pass filter that just so happened to be unstable. However, I placed that unstable device under test in a negative feedback control configuration as you see here, and that stabilized the overall system, which allowed me to make measurements upon it, like the transfer function measurement we see here. This measurement consists of perturbing the controller output with some small signal, and then I make two measurements. I make the measurement of the input to the device under test and the output of the device under test. With those three signals, then I can compute two cross spectrums between the excitation and the output, cross spectrum between the excitation and the reference or input to the device under test, take that ratio, and that forms a pretty good, pretty reliable transfer function estimate of the system. So today, in this video, we're going to apply that same measurement technique to a buck converter. So I would recommend that video as a precursor to this one, because in that video we go into more detail under the hood of how that technique works. Today the focus is really just on how we can apply the technique. Okay, so in today's example we have a buck converter, and the buck converter consists of an inductor here in series with a parallel RC combination. Now this just so happens to be modeled using Simscape components, a library of Simulink. And then in front of that LC circuit, which just so happens to be now a second order circuit instead of a first order circuit like before, we have three additional components. We've got an active switch, a passive switch, and a voltage source. The active switch in practice would be something like a MOSFET. That's going to be either turning on or off, and then a passive switch is, as shown here, would be a diode. Now of course this could be an active switch as well. We're just using the more basic configuration of the buck converter. And of course in any circuit you could have more impairments in the circuits you'd be modeling. This L1 here could have series resistance or parasitics, could have parallel conductances, it could have tolerances, it could have other, shall we say, effects or impairments on it, and the same way with the capacitor and the resistor. If you wanted to add resistor noise, if you wanted different capacitance models, the way you model it, whether it's a straight constant value or some type of lookup table, etc., and the same thing with the parasitics. We could add all those in here, optionally remove them if you wanted to. Same with the diode and switch if you wanted to add more detailed models of those. But in this case, we're just starting simple. We've got a basic buck converter circuit configuration, and we'll be driving this with a PWM signal. So essentially some type of pulsed on-off signal between, essentially you could say between a 0 and a 1. And the only thing that's going to vary on that signal really is how long it stays high versus how long it stays low. It's so-called duty cycle. And that is, again, that's modeled by this behavioral PWM subsystem where we have our clock driving a resettable integrator. So this is integrating up, and when it integrates up past a certain threshold, denoting controlled by our duty cycle setting, it's either going to go high or low depending on when we cross that threshold. Okay, so the longer the output signal is high, the higher the voltage is on the output. All right, and this is connected in a negative feedback configuration. We measure the output load. We measure the voltage across the load. We compare against our 12 volt set point. You could change that set point to anything you wanted to, and depending on that difference, the PID controller, whether we're above or below that set point voltage, we're either going to increase or decrease the duty cycle to again become more in line with that 12 volt set point. And this switch here, I'm not using it right now, I've just got it in closed loop, but if we wanted to run the test in open loop, I could just set some fixed duty cycle there. Of course, we have to limit our duty cycle. A duty cycle can never become more than 100% or less than 0%, so that's the purpose of the saturation block there. Okay, so effectively, when we go back to the main circuit of interest here, most of the dynamics here are in this buck powertrain block, at least the ones that we're trying to characterize. You could think of this as two separate circuits, depending on whether this switch is closed or open. And I've drawn that right here in a separate diagram, separate window. When the switch is closed, where again the switch would be right here where I'm highlighting, then we're charging this inductor using our 30-volt input charging source, which in turn is delivering current to our load. Now in mode 2, when we turn the switch off, deactivate it, at that point now we have effectively almost a parallel RLC circuit. Now I say almost because actually there is a diode drop here in this section of the circuit, which I'm not showing, but yeah, you would have some small diode drop here in series with your resistor. And of course, if we were modeling parasitics and other effects in the model, those would be included in the simulation. Here I'm just showing the basic topology. So we're going to be switching between these two modes of the circuit controlled by that PWM output signal, which is in turn controlled by the controller in a feedback loop. Let's go ahead and run this model and get a feel for how it runs first. And we'll view our output voltage here. And what we'll see if we zoom into the first part, we see it has some overshoot above 12 volts, and then it starts to settle down to steady state. And I'll go ahead and hit stop since we're pretty much in steady state now. And we can see again the transient response. And then we go to the end of the waveform near steady state. We'll just zoom in maybe around there, do an auto vertical zoom, and zoom more horizontal again. And we'll see we've got some variation, some ripple about our 12-volt set point, as is expected for any switching converter like a buck converter. And in this case, it looks like we've got about 7.88 millivolts or so peak-to-peak ripple around our 12-volt set point. So not too bad. And it just so happens that frequency also has, you see it's sinusoidal variation. The frequency of that ripple is right at 50 kilohertz, which just so happens to be, no accident there, our switching frequency of the PWM. So if we go back to that clock, which is driving our resettable integrator, the rate on that pulse generation is 50 kilohertz. Okay, so that's the reason we see the ripple at 50 kilohertz versus another frequency. Okay, so now the question is, how do we measure the transfer function, let's say, of just the PWM plus the buck converter? So in other words, an open loop response while the system is running in closed loop. Of course, you could always try breaking the system apart and driving it separately in open loop, but in many cases that's impossible, and or you just want to make the measurement in situ as it's normally operating. And that's what we're going to do here. We're not taking and breaking the system apart and measuring the PWM and buck converter in isolation. We're going to be measuring it as it's normally used, as normal operation, as a buck converter with a controller in the feedback loop. But yet when we make the measurement, let's say we don't want to include, let's say the PID is part of that measurement, and we just want to include the transfer function from the duty cycle input to the V out of the buck converter. Okay, so that's really our task. The way we're going to do that is by injecting a small signal perturbation at the controller output. Now you might ask, well, why not just monitor the signal at the duty cycle input here, monitor the signal that we've measured across the load resistor, which we're kind of already, well, we just got a go-to tag on it now. Monitor these two signals, perhaps take an FFT of them like we did before with our cross-spectrum, auto-spectrum based measurements, and then compute a transfer function from that. In other words, just let it run a normal closed loop operation and just log the signals, take FFTs, and compute a transfer function. It turns out, in this case, that's a little too simple and it doesn't work because this signal and this signal are very narrow band. As we saw earlier on our I can't remember if we zoomed in on this one or not, but if we do that, what we're going to see is this is pretty much just a sinusoidal input or excitation at this point, and you cannot just use a single frequency to measure a transfer function. Also, this single frequency happens to be 50 kilohertz, the switching rate, which is way too fast for the bandwidth that we're interested in characterizing the buck converter over. The buck converter, most of the dynamics are in, let's say, the 0 to 10 kilohertz range for this particular buck converter, and the switching frequency is usually a magnitude or so greater than the buck converter itself bandwidth, or at least the dynamics of interest here. So this frequency here is not going to be of any use anyway, and even if it were, it would only be one frequency. So we're kind of back to the drawing board. And again, that's where our double cross spectrum transfer function measurement comes in. What we're going to do again is inject that small signal perturbation here, and I'll uncomment these blocks and uncomment the summing junction. And what we'll have is an excitation. In this case, it's going to be a very low-level random noise signal. It's going to perturb our controller output. That will drive the saturation block, in turn driving the PWM. And then we will have, we also have to make two measurements. We're going to measure the voltage output of our buck converter. That's V out here, which in turn is a go to from tag here. And we have to measure the input to our device under test. That's the duty cycle. All right, so now we have something more like a complete measurement. Now let's look at the configuration of this system. It happens to be, we're going to measure over a 10 kilohertz bandwidth using 10 millivolt level of excitation for our random noise. It could also be a chirp. We're going to take 512 FFT points. That's going to set the resolution effectively of our measurement, how low a frequency we're interested in characterizing. And we're going to take 10 averages. If there's any noise in the system, we'd like to minimize it. And we have a 30 millisecond hold off time to ignore things like any startup transient in the system. Okay. So from using those parameters, we could also compute some type of meaningful stop time. So we could say, well, our bandwidth is 10 kilohertz, our FFT size is 512. So we could do something like this. We could say our FFT size is 512. We've got a 10 kilohertz bandwidth, but we're going to oversample that. And I just so happen to know that our oversampling rate here is 2.56. So that says each FFT is going to take 20 milliseconds. If we did 10 of those for 10 averages, we would take 200 milliseconds. And of course, let's just throw in some extra slop for good measure, since this doesn't take too long to measure, or we could just make it 200 milliseconds. We'll run this for 200 milliseconds, again, perturbing it, but we don't want to, again, perturb it too much. If you perturb it too much, then you're going to go into a nonlinear state. You're going to be moving operating points of the system, which kind of blurs the measurement at any particular operating point. And so we want to avoid that, but we also don't want to drive it too gently. If there's measurement noise in the system, we want to get a decent signal noise ratio. So here in the upper right is our magnitude response measurement of just, again, the PWM and the buck converter, while measured in closed loop, but isolating just the open loop response of those two blocks. And then we've got our phase response on bottom. Now, at that point, you could claim victory, and perhaps we have achieved victory as far as the goals we set out to achieve. But of course, you'd always like to know if you're on the right track with your answer. And that's where some pre-work, offline theoretical work comes in very, very handy to see if you're on the right track. Now, in this case, I just so happen to leverage Symbolic Toolbox for that purpose. And I've got a script which runs after my simulation, which compares theory versus measurement. So you see here I've got the analysis in red and the simulation Simulink model results in blue, and they're overlaid on top of each other, both magnitude and phase. Now the details of this derivation, which are based on an average state space modeling technique, are beyond the scope and the time limits I've set on this particular recording, but I just want to throw it out there that of course you always want to compare against theory or some type of formal analysis whenever possible. In many cases, of course, you can leverage maybe some paper that's already done the work. But in many cases, of course, you may have a novel circuit and you need to derive something from scratch, and that's where a tool like Symbolic Toolbox can come in handy. I've also shown here for this buck converter, there's a paper by TI which also did the derivation. It's called Understanding Buck Power Stages and Switch Mode Power Supplies. And then if you scroll down in that paper, and now I forget which page it was on, I just scrolled quickly scrolled past it, but in this paper it derives many of the transfer functions for different operating conditions like continuous conduction mode and discontinuous conduction mode. Again, is a good starting point. It's always good to have a document like that to help out. All right, that's about all I wanted to say on this exercise. I hope you found it helpful. Again, on another application for using the double cross spectrum transfer function measurement on a buck converter. Thank you, and signing off now.